Hi everyone, thank you for coming to my virtual talk at WINE 2020. I will be talking about the paper Beyond the First Welfare Theorem, Counteracting Inequality in Markets. And this is joint work with my advisor Ashish Goel, both of us at Stanford University. The main takeaways for this talk are going to be the following. First, we're going to talk about how linear pricing can lead to inequality. We're also going to cover how nonlinear pricing can solve this for a wide range of utility functions. We will cover how this relationship can be quantified using CES welfare functions, which is going to generalize the first welfare theorem. And finally, we'll discuss how this relates to nonlinear pricing in the real world. We'll start with a motivating example. So imagine 3 different people who all want water. Linear pricing means that buying X units costs Q times X, where Q is some price. So we have 3 different agents. They're each going to have a valuation, which here is just represented by one number, WI. And they're going to try to maximize WI times X, which is their value, minus Q times X, which is the cost. This is called a quasi-linear utility. Some of you may be familiar with this. So fairly standard model so far. Market equilibrium is when the demand, what the agents want to buy, exactly equals the supply. So what happens if we set the price Q to be larger than 6? If this was an in-person talk, this is where I would turn it to the audience. But since there is no audience right now, I will just tell you. So if Q is greater than 6, what's going to happen is no one's going to buy anything because no one is willing to pay that much. If Q is less than 6, agent 2 is going to basically want to buy infinity. And then finally, if Q is equal to 6, then agent 2 is going to buy the entire supply, and the other 2 agents will be sad because they get nothing. This is also the unique market equilibrium. We'll talk now about the first welfare theorem. In the previous example, what happened was the agent that valued the good the most got the entire good. And this is going to maximize the sum of valuations, also known as utilitarian welfare. This can be seen as the most efficient outcome. And the first welfare theorem tells us exactly this, that for linear pricing rules and quasi-linear utilities, all of the equilibrium allocations are exactly the allocations maximizing utilitarian welfare. So what this essentially tells us is linear pricing is going to always give us the most efficient outcome. And we can formalize this a little more by saying any allocation X maximizes utilitarian welfare if and only if there's a linear pricing rule making it a market equilibrium. And we also saw that for a single good, the price becomes the maximum anyone is willing to pay, right? So in the previous example, the maximum value was 6 and the price had to be 6. And what this means is that the good goes entirely to people willing to pay that amount. Everyone else is priced out of the market. This has a lot of parallels in real-world economies, like with gentrification, for example, where the wealthy people get to dictate the market price, and everyone who can't pay that much gets priced out of the market. And this leads to inequality. So we may be wondering if capitalism and equality are fundamentally at odds, or if there's any way that they can work together. And in this talk, I'm not really going to make either of these claims because it's a very complex issue, but I do want to show one way in which they can maybe be brought closer together. And you guessed it, nonlinear pricing. Specifically, we're going to work with convex pricing. This is used actually in the real world a lot for water, and we'll continue to use that as our example. So what this means is that it becomes easy to buy a little bit, but hard to buy a lot. And intuitively, this should prevent any individual from dominating the market by buying everything. We want to note that this is still anonymous, meaning every agent who buys the same bundle would pay the same price. And we're not basing the price at all on people's identities, just based on how much they buy. And like I mentioned, this is actually used in the real world for water pricing all over the world. We also see it a bit in electricity and some other resources like that. And in all these real-world examples, people often say that this convex pricing promotes equality. But it's never really clear exactly what that means. So the idea in this paper is we're going to try to quantify exactly what this relationship is between equality and efficiency in convex pricing. Let's introduce a bit of mathematical notation. So we'll work with m divisible goods. They each have some fixed supply, n agents. Each agent has a quasi-linear utility function. So that's going to be, they want to maximize their valuation, denoted vi of xi minus their payment. Xi is the bundle they receive, and xij is the fraction of good j that agent I gets. He is linear if it has a single price for each good, and then we just sum up the price across goods. And this is sort of a very standard market model for quasi-linear utilities. Next, let's talk about CES welfare functions. So this is how we're going to formalize the notion of equality. In general, a welfare function says how good each allocation is. And a CES welfare is a particular family of welfare functions that takes a parameter rho between -infinity and 1. And the CES welfare with respect to rho of a given allocation is defined as you can see there. It's essentially a power mean with respect to rho. Some of you may also be familiar with the CES agent valuation. So you can see this takes the same mathematical form, but conceptually, that's referring to how much an agent values a particular bundle, whereas the welfare function is referring to how good for society we think an allocation is. This is another place where in in-person talks, I would ask the audience to chime in here, but basically this is a table that shows for different values of rho, we're able to recover some very common welfare functions. So when rho equals 1, CES welfare just becomes a sum of utilities, and this recovers the standard utilitarian welfare function. If we take the limit as rho goes to 0, it becomes a product of utilities, and we get Nash welfare. Rho goes to -infinity, becomes a minimization, and we get egalitarian or maximum welfare. We can put these on a sort of plot where we think of egalitarian as only caring about equality. When you're maximizing the minimum utility, you're essentially going to end up with a situation where everyone has the same utility. And we can think about utilitarian as the opposite extreme, where you only care about efficiency. And what CES welfare does is it creates this smooth continuum all the way from pure equality to pure efficiency. And we talked already about how linear pricing is going to put you all the way on one side of the spectrum, and with utilitarian welfare, which only cares about efficiency. Just want to briefly mention that CES stands for constant elasticity of substitution, which basically refers to a mathematical property that this functional form has. Okay, so this takes us to our main result, maximizing CES welfare using convex pricing. And to state it, we just need one definition, which is that a valuation is homogeneous of degree R if scaling up the bundle by some constant C scales up the valuation by C to the R. So this is our main result. Let's assume rho is between 0 and 1. And we're going to assume valuations are concave, differentiable, and homogeneous of degree R. Those are our assumptions. Then there exist real number constants, Q1 through Qm, one for each good. And we define the following pricing rule, where we sum up across all the goods of Qj times Xij, and then we put that all to the 1 over rho power. So if you have this pricing rule, then every market equilibrium will maximize CES welfare with respect to rho. And that's the same rho for CES welfare as is in the pricing rule. A slightly stronger version is we have the same assumptions on valuations. That should say 2020. And an allocation X maximizes CES welfare with respect to rho if and only if there exist these constants such that the pricing rule defined there makes it a market equilibrium. So basically what this is saying is once you commit to a particular value of rho and you commit to this functional form, then all of the market equilibria are going to exactly maximize CES welfare with respect to that value of rho. One way to interpret this is basically saying, as a social planner, we want to pick our desired equality efficiency trade-off. So pick a value of rho, then put an exponent of 1 over rho in your pricing rule, and you'll be guaranteed to get CES welfare with respect to that value of rho. So you'll be guaranteed to get that equality efficiency trade-off. There's also a reason why this doesn't work for rho less than 0. It's a little complicated. We don't have time to get into it now. But for our purposes, we can think of rho going to 0 as being the most equal, and rho going to 1 being the rho equals 1 is still utilitarian welfare, which is the most efficient. So I want to briefly claim that this is qualitatively the right pricing rule, and this is what I mean by that. As rho gets smaller, so it goes to 0, the pricing rule is going to become steeper. And we can see this for a single good quite easily. For rho equals 1, that's just our normal linear pricing. Rho equals 1/2, it becomes easy to buy a little bit, but harder to buy a lot. When rho is 1/5, we can see it's quite easy to buy all the way up to here, but then it starts to get much harder. And for rho equals 1/10, you can actually buy all the way up to here and pay very little, and then the price shoots up very quickly. So in this rightmost example, what's going to happen is probably all the agents are going to end up with bundles kind of around here, the same in a similar range. And this is kind of this is one way to interpret the idea that as rho goes closer and closer to 0, we get more and more equality. In this case, we're talking about equality in the allocation. And like we said, the smaller rho is, the easier it is to buy a small amount, and the harder it is to buy a large amount. We can easily relate this back to the plot I showed before, where rho getting smaller is more equality, rho going closer to 1 is more efficiency. And as you carefully tweak the value of rho in your pricing rule, you're going to smoothly slide along this continuum. So, quick note on QJ. That's a constant that kind of represents how much society cares about good J, both absolutely and relative to the other goods. For those who are familiar with convex programming and all of that, it's going to be an optimal Lagrange multiplier for good J in a convex program for maximizing CES welfare. And for people familiar with the Eisenberg-Gale program, this is going to be very similar conceptually to that. Okay. The last thing I want to talk about is that there's a potential implementation issue with what we've discussed so far, and that relates to Sybil attacks. So a Sybil attack, if people aren't familiar, is when an agent can pretend to be multiple different identities, or and you can see here we have an example of a woman with multiple personalities. It's named after Sybil Dorset. An agent with multiple identities can try to manipulate the system. And convex pricing is very susceptible to Sybil attacks, because if I can split my purchase across multiple identities, I will lower my costs. So in order for this to work, we have to have some way of keeping track of people's identities. And Sybil attacks are a whole area of research in general. This is also something that has been discussed in terms of convex pricing specifically, since it is used in the real world. And there are different solutions. Some of them work better than others. For water, each house has a particular identity. Each house will have a specific water meter. And so, sure, you could go to your neighbor and ask your neighbor to buy water for you and carry it back to your house, but that's pretty inconvenient. The issue actually often comes the other way, where especially in poorer areas, you'll have multiple families sharing a single water meter, and actually that can end up with them paying a higher price than they should. So there certainly are implementation issues with regards to convex pricing, and these are issues that are encountered in these real-world implementations. So my goal here isn't to claim that convex pricing is the be-all, end-all. There certainly times where it wouldn't work, there are times where it would work, but I think this is a good alternative to consider to the standard linear pricing. To wrap up, we talked about how linear pricing maximizes utilitarian welfare, and that can lead to inequality by allowing the most wealthy people to price the poorer people out of the market. Nonlinear pricing, and in particular convex pricing, can remedy this for a wide class of agent valuations. Remember that the only assumptions we needed were differentiability, concavity, and homogeneity of degree R. And we can quantify this relationship with CES welfare functions, where the slope or curvature of the pricing exactly corresponds to this equality efficiency trade-off. And this gives something of a quantitative interpretation of this equality thing that's often talked about with regards to these real-world implementations. So what does equality actually mean? This is one interpretation. For future work, one thing we didn't talk at all about was how to actually compute these prices. And we have some results on this in the paper. We have a sort of iterative algorithm based on convex programming. But what would be really interesting is some sort of tautonment, where on each step, you can show the agents the current prices, and they report their demand given those prices, and then you adjust the prices. So I think a tautonment for this would be very interesting. Another interesting avenue could be approximation by piecewise linear pricing. So in all the real-world implementations that I'm aware of, they use a piecewise linear approach called usually at several different tiers, where the first tier you're going to pay one linear price, the next tier you'll pay a higher linear price, and so on. I think this is probably for implementation use because consumers might not be as clear if you tell them, okay, well, here's this functional form that's going to determine how much you pay. So if we want to make this at all practical, it would be very interesting to show if using a piecewise linear approach, you can still get some approximation of the CES welfare. So what I would love to see would be a result like if you're allowed K pieces in your piecewise linear price curve, you can get some approximation of the CES welfare where K shows up in the approximation ratio. Another important direction is revenue. So if my goal in this talk is to convince sellers to use convex pricing because it will be more equal, which is not necessarily my goal, but if we want people to actually adopt this at all, sellers are going to want to make sure that their revenue won't be impacted or won't be impacted too much. So I think trying to understand how much revenue convex pricing will give, especially with respect to row, I think is important. And finally, I didn't talk at all about indivisible goods. So this was entirely about divisible goods. It's going to be a little different, but I think a similar type of functional form can be used, and qualitatively, the intuition should be similar. So far, we haven't had any success really proving anything formally about it, but I think there's definitely some future possibilities there. That is all. Thank you for coming to my virtual talk, and have a good rest of the conference.